Hi and welcome to a related rates of change question. This example shows us the relationship between several variables within the one question, and it's difficult not because of the maths but because of the number of steps involved. So we should always start with a diagram of what's going on. So here we have a bucket in the shape of a cone. And this time, rather than being told the height and radius of this shape, we've actually just been told the angle at the vertex. So it's slightly different to what we've been doing in class. But anyway, it's a cone. And what we know is that this angle down here is 60 degrees. And Adam's going to place this cone under a bucket and it's going to fill up with water. So the water is then going to start doing... We'll choose blue for water. The water is going to start filling in from this tap, and the level of the water is then going to do this. We have a radius of r and a height of h, and this angle just in here obviously is half of 60, so we're going to have an angle there of 30 degrees. So we actually end up with this little triangle RH and 30, which will help us later on try and get a relationship between these variables. Like any related rates question, remember we've been focusing in on two questions. What do we know? So what does the question tell us, and what do we want to find? So the rate that we actually know when we read this question is that the tap is filling up the bucket at a rate of 10 centimeters cubed per second. So remember, even the units give you a clue of what rate that is. So we actually know dV dt is equal to 10. And what we want to find is the rate at which the surface area is changing when the radius is 5. So we actually want to find dA dt. That's the one that we are looking for. So like any chain rule, we should always set up that chain rule that helps us find this unknown rate. So dA dt, remember one diagonal is the dA on the top there and the dt down the bottom here. And then this diagonal going the other way needs to be something that we actually know. So in this case, we know something about the volume, so dV and dV. So this one gets a tick, we know that, that's actually equal to 10. But this one here, dA dV, we actually don't have any expression that relates area to volume or volume to area. So we need to start thinking, it's a cone, what do we know about the cone, and work on those rules there. So what we know about a cone is, volume of a cone is 1/3 pi r squared h, and surface area of a cone, not a very common rule that you use, so one that's worthy of putting in your bound reference, is pi r squared plus pi r by the square root of h squared plus r squared. So these two rules, just looking at them, we can see here we've got volume, but in terms of radius and height. And we've got area also in terms of radius and height. And we know that we can't differentiate either of these expressions until we get them in terms of just one variable. So we need to work on that. If I come back here to this chain rule set up here, to find this one here, I need to set up another chain rule. So what I'm saying is, to find dA dV, I can actually say, well, dA is on the top, dV is on the bottom, and what do I know that would go on this other diagonal? When I look at the two formulas, I've got volume in terms of possibly radius or height, and area in terms of radius or height. So if I rearrange those expressions just in terms of radius, I would potentially be able to find dV dr and dA dr. And that's my aim. Both of these expressions, if I replace them with a variable of just r, so in other words, look for something that I can replace h with in terms of r. And that brings me to this little triangle that we had up here at the beginning. So using that triangle, I know that tan of 30 equals r over h. So h would be r over tan 30. And this brings in your exact values. So this potentially could be an exam 1 question, because tan 30 you're expected to know is 1 over root 3. So therefore h is actually root 3r. And then I can put them into both of these expressions up the top here. I'll just change colour so it stands out. So here now I can replace the h with volume equals 1/3 pi r squared and then times root 3r, which gives me root 3 on 3 pi r cubed. And into the area one, I can replace h as well by saying, well, it's pi r squared plus pi r by square root of root 3r squared plus r squared. Now work with this. You get pi r squared plus pi r by, now this in a bracket squared means everything inside that bracket is raised to the power of 2, so it becomes 3r squared plus r squared, and then that simplifies to square root of 4r squared and I can take the square root of both of those terms, the 4 and the r squared, to give me 2r, and then that simplifies to 2 pi r squared, and then put them together because they're like terms, gives me 3 pi r squared. So I actually have area equals this, 3 pi r squared, and I have volume equals this expression here. And both of those now are volume in terms of radius and area in terms of radius. So I can actually differentiate them now. If I say dv dr, I could use that to put into this part of my chain rule. And if I say dA dr, I can use that to put into this part of my chain rule, all in order to find the dA dv that I need. So that's what I'm going to do. I'm going to differentiate each of those terms. So I have dv dr equals root 3 pi r squared, and dA dr equals 6 pi r. And I'm going to put them into here. So I get dA dv equals 6 pi r, and then this one, remember, is the reciprocal of this. So it's 1 over root 3 pi r squared, which breaks down to 6 over, now that pi cancels off with that one, that r cancels off with one of those, so root 3r. And now I need to go back into this original chain rule that we set up at the beginning. So I have now dA dv is equal to this expression here, and dv dt we knew from the very beginning was 10 centimeters cubed. So I'm just substituting that now into dA dv was the 6 over root 3r, and the dv dt was the 10. So I get 60 over root 3r, and then the original question said, let's come back up here, find the rate at which the surface area is changing when the radius is 5 centimeters. So I'm now going to substitute the 5 for my radius, and I get 60 over root 3 times 5, which is 12 over root 3. So my final statement, therefore, is that area is increasing, because it's positive, at a rate of 12 over root 3 centimetres squared, because it's area per second. So you can see that the actual maths, hopefully, the fact that we had to differentiate two expressions was not difficult. The hardest thing there was the number of steps, because when we set up this original chain rule, we actually didn't have the dA/dV information, and then we had to do a separate chain rule to find our dA/dV using the two rules that we know about cones, one for volume, one for area. And then rather than doing the similar triangles like we've done in class when we actually know the radius or the height of the original cone, this time we knew the angle, and so we used our SOHCAHTOA sine cos tan and our exact values. So hopefully that gives you an example of a related rates where it's a double chain rule. Hope it helps, and good luck with the rest of your revision.